Hi everyone. In this video we're going to talk about leading and lagging sine waves. So I'm going to draw three sine waves in relation to each other. Wow, these axes are not straight at all. Let's try that again. So when you're dealing with AC circuits, at some point you may find that you are looking at more than one sine wave at the same time, and that these sine waves are shifted in time related to each other. So I'll keep the heights of all the sine waves the same at V peak. This is this is wave A. So wave A is VP sine theta. So let's think about these first in terms of just angle as the horizontal axis instead of time. So A is VP sine theta, right? A sine wave where the sine wave is 0 at 0 and it starts from there and it goes forward. Now if I draw another sine wave, maybe not blue, let's make this purple. So here's another sine wave B, and it has the same frequency as sine wave A, but it has been shifted in time, and I've given it the same amplitude at V peak for now as well. So waveform B is shifted by some angle. I'm going to call this angle phi. Okay, so some angle phi it's been shifted by. Its equation is going to be VP sine theta minus phi. Okay, whatever that angle is. And when you are using this type of equation with actual values, say this was some angle, say this was 60 degrees, right? Well, this would be the 60 degrees. This right here would be wherever you were wanting to find the value of waveform B. So if you were here at this theta wanting to find the value, that's the value you would put in for theta, but you would have to subtract this 60 degrees because waveform B started its zero crossing point at 60 degrees instead of at 0 like a regular sine wave. Okay, so this is a shifted sine wave. And so let's look at another sine wave, waveform C. Not going to draw this very well, but there's waveform C. I'm assuming it also has the same V peak amplitude, and now it has been shifted the other way. So it is actually plus, we'll say phi 2. This is angle phi 2. Oh, phi 2. Okay, so we say that waveform B, now we want to say whether it leads or lags waveform A. The waveform that crosses 0 first in time, going negative to positive here, crosses the 0 axis, is the waveform that happens first. So when we're looking at the 0 axis in time, if I travel from left to right, like this, I hit waveform C first, then A, then B. So C leads, then A, then B. Okay? And so if I were to write that down, I would say waveform B lags waveform A, and waveform C leads waveform A, because we see it first in time. Okay, let's just finish off a numerical example here, so you can, a simple one, so you can see how these values would calculate. So suppose I wanted the, I'm on the eraser, hang on a sec, I gotta draw waveform B again. Or can I undo? Oh, I can. Excellent. Okay, so get my pen back here. Waveform B. I want to know the value of waveform B at 150 degrees. Okay, I want to know what is the instantaneous value here of waveform B. So I know that this value should be equal to V peak times the sine of theta minus phi. And remember, this theta is angle where I want the value, and this phi is the angle of the shift. So when I plug these values in, this is going to be Vp sine 150 minus 60, because 150 is where I am, where I'm calculating the value, and 60 degrees is this how much this sine wave is shifted by. And so I see that's going to be Vp sine 90 degrees. So with my calculator in degree mode, I'm going to find out that the sine of 90 degrees is 1, and this answer is just V peak, which is the same as any of these, like as the same as waveform A, also at 90 degrees, right? So you can see that this is sort of looking like if I shifted waveform B back by 60 degrees, it would line up with A, and this point would be at 90 degrees, right? And we can see that when we do this little math here, where we subtract the shift from the angle that we're at. Okay, so that's leading and lagging sine waves. Just something to keep in mind.